We are on our last piece of chapter 13, and we're going to look at hypothesis test for the difference in two means. And we'll come to this stuff later. So let's give you a big intro to what we're talking about. I want you to imagine that you have two populations, population 1 and another population 2. And we want to see if there's any evidence to prove that the mean of this population is in some way or other different than the second population. Right. So mu1 is the mean for this population, mu2, we'll call that the mean for that population. And let's do weights. So population 1 is going to be America, and we got a sample of 100 Americans, and the mean weight was 180 pounds. And we went to Scotland and we got 200 of those guys, and the mean weight of the Scottish people was 190. And so we are looking at these two, and the raw data suggests that Scottish people are heavier than Americans, at least in this story, right? But we want to see if we can set up a hypothesis test to actually prove that that's true. Now, there's one other piece of information I need to give you, and is that the standard deviation of that one is 15, and say the standard deviation of this one is 30. So how do we set up a hypothesis test when you have two distinctly different populations and you're trying to measure, is there evidence that there's a difference? Well, the first step is the null and the alternate hypothesis. The null hypothesis is that they're both equal, but we don't normally write mu1 equals mu2. We say mu1 take away mu2 equals 0. You see that? Isn't that the same as P1 take away P2 equals 0? Remember when you compare two proportions, you set it up the same way. Now, in our particular one here, aren't we trying to say that Americans are lighter than Scots? So that would be the difference is less than 0. Why? Look, smaller, right? Less than 0. Now, there are three versions. There's a less than version. Can you imagine that, whoops, can you imagine that sometimes you want to prove that the first thing's bigger than the second? So that would be a greater than 0. What would be the third and last type of comparison? Is it less than 0, right? Is the first thing less than the second? Is the first thing bigger than the second? What would the last one be?
Not equals to 0.
Not equal to.
Different from or not equal to?
Different from or not equal to, yes, Cody. Right. So that is pretty standard, isn't that? Every hypothesis tested the same three choices, right? Is the thing bigger than, is the thing less than, is the thing not equal to? And whether it's a single proportion or mean, or whether it's a difference between two different populations as it is here, it's still the three main situations. These two are called one-tailed tests, and this one is called a two-tailed test. And once you've got that set up, you'd also have a significance level, and let's just call it 5% as always. Now, there is a little bit we can do by hand, but most of what we're going to do is going to be done using SOLE. But I can do a little. There is a test statistic that we can find. It's this guy. And in samples where you're comparing two different populations as we are here, you're really going to be looking at a t-distribution, right? So it's a t. So the test statistic is a t. And it's given us the difference between the two means divided by the standard error of the difference. And the standard error function is this guy. Do you recognize this guy? You remember seeing this guy somewhere before in a different context? Confidence intervals for the difference between two means. That's the same formula. Well, let's do this test statistic. T. It is x1 bar, take away x2 bar, divided by the standard error of x1 bar, take away x2 bar. So I'll need to find the standard error, and then I'll plug the numbers in here. It's the square root of this guy squared plus this guy squared. So the standard error of the difference is 15 squared over 100 plus 30 squared over 200. See what that ends up being. 15 squared divided by 100 plus 30 squared divided by 200 ends up being 6.75. I don't need to do that. I could have just done it in one go, but I've got it now. And the answer we got is 2.598 roughly. So I can now get the test statistic. It is this guy, 180, take away this guy, 190, divided by 2.598. I'm going to do this in the calculator, I'll need brackets. 180 take away 190, divided by 2.598. And the answer I have here is negative 3.85 to 2 decimal places. So you can get a test statistic, provided you know the two means, the two standard deviations, and the two sample sizes, right? The t-score is very like a z-score. Remember, z-scores are interesting. Outliers, for instance, when the score gets 3 or bigger or negative 3 or less. And you see that's negative 3.85. That's got a very good chance of proving that these are different, right? That is a very good chance. If the t-score was negative 1.4, I don't think you're going to get any, it's going to be not enough evidence. If it was minus 30.85, you could probably sell your house on it and be safe. Right, that's how sure you'd be that you've got the evidence that you want. So far, so good. Right. Now, the next stage of this process, so I'm actually going to go through the whole process and then we'll go to the homework. And they do that little thing where they do a little bit and then a little bit more, and it's only the last 3 or 4 questions where they do everything. But we're just going to go through the whole process once. Up to here, you can do it by hand. Everything after here, you must use salt. The only thing that are left is p-value and then your conclusion. So I'm going to nip over to salt. And just because, I don't know, are you looking at chapter 13 here? Okay, just because there isn't a salt button on your question doesn't mean you can't use salt. Yeah, just find a salt button, anyone will do. I'll click on that one. And now we are going to find the p-value. Make sure you're in inferential statistics. And over here, can you see 2 sample t? And here you put the first group. So that was the Americans. So the Americans had an average of 180. The standard deviation for the Americans was 15. And the sample size was a really reasonable 180. Now the second one, the Scottish guys, they were.
You put the sample mean for the first one wrong. It's 180, not 189.
Where's that 9 come from? Thanks for catching that. 190. Standard deviation was 30. And the sample size here was a bit bigger, 200. Okay, so you comfortable?
Your sample size is also incorrect for the first one. It's 100, not 180.
God, I'm good today, aren't I? Right? Are we comfortable if you read the question and you hit the right buttons that you'll get the data into the software? Hypothesis test. You notice the difference says 0. That's what we want, right? That's H1, mu1 take away 2. And we want to prove, in this case, it was less than, didn't we? That Americans were less than Scottish. And I should be able to generate results. And do you remember that standard error that I calculated? Do you see it's there? 2.589. Remember 2.5? That guy? Got that one right? And if I look a little bit higher, can you see the T statistic, that negative 3.8 guy? 3.85. Now, so basically, couldn't have used SALT to do all of those early stuff that I did by hand. Right? Couldn't have used SALT to find the standard error. Couldn't have used SALT to get the T-score as well. But that's cool. Now, the p-value we got was this number here. And that's 0.123, 4 zeros and a 7.3. And that's where the p-value is. And now I'll return back to the whiteboard. And we'll do our test. And our test will be, is the p-value less than the significance level alpha? Is this 0.123, 4 zeros and a 7.3, is it less than the 5%? And this is definitely a yes. And conclusion time. Aren't there lots of different ways that you phrase the conclusion? Here's a couple of them. Couldn't we say, for instance, I'll put it down here, that there's enough evidence to reject the null hypothesis? Right. Couldn't we also say there's enough evidence to prove the alternate hypothesis? Couldn't we have said there's enough evidence to prove that Americans weigh less than Scots people? And I'm running short of sentences, but haven't you found some other ways that they ask you to describe what that means, right? And that's the end of the process. In this case, we have collected enough data to prove that Americans, on average, are lighter than Scottish people. At least based on this evidence, right, if this was true. Any questions about that process? Because it does, isn't it very like all the other hypothesis tests in a lot of ways? Right? It has that same kind of flow.
I feel like the confusing part is what comes after we have enough evidence to reject, because then I feel like it gets technical after that. It's like,
yeah, it's like the lawyers got involved in the answer, isn't it? Because they phrase it in such weird, sometimes they phrase it like it's a double negative. There's enough evidence to not reject something, and I'm going, what does that mean again? Yeah. You just have to read them carefully when they do that to you. This one's for later on. So let's go back and now show you, if I can find the, hold on a second, I've lost something. I've lost my question. Yeah, okay, there we go. So I'm going to basically return to the start of WebAssign homework and show you the first couple of questions only take you a little bit of the way, right? You don't really get to do the whole story to the last half, and there's only 9 questions, so there's not a lot of questions anyway. Now, okay, we've got the answers here. We'll just keep the answers and talk through this, why that is the answers then. For each of the following research questions, specify whether the parameter of interest is one population mean, or the population mean of a paired difference, which we don't worry about, or the difference between 2 populations. Okay. First story, residents of a neighborhood have been complaining about speeding cars. The speed limit is 25 miles an hour in their area. The local police monitor the situation by recording the speeds of 100 randomly selected cars. And what we want to know now is whether the mean speed of all the cars that drive through the area is 25 miles an hour. Right. Okay, that's the story. Can you see that this is a story about one population mean? Right, this street that has a 25 mile an hour limit, that's the population, right? Cars who use that street. Now in part B, after collecting the data, the police decide to install an electronic roadside sign. I've seen, there's actually a couple around this area. I've seen them. Do you know the ones when you drive up, it says you are doing 40 and the speed limit's 30 and it tells you too fast? One of those things. And so the police decide to install one of these, and they hope that what that's going to do is reduce the speed, right, of the cars that are using that street. And so they record another different cars, I'm assuming, 100 randomly selected cars, and they want to know where the mean speed is lower after the installation of the sign than it was beforehand, right? So let's say before that sign, electronic sign thing went up, the average was 27 miles an hour, right? And then they put it up and the average goes down to 24, right? Wouldn't that be a good indication? Keep the sign, it's doing its job, right? If it was 27 before they did it, and it was 26.8 after they did it, wouldn't that be an indication that that sign has no effect on what's going on, right? Because you wouldn't be able to get any evidence out of such a small difference.
What would be an example of the population mean of paired differences?
Imagine you wanted to do husband and wife, and you wanted the man's age and the woman's age. So what you would do, instead of recording your age or your husband's age, you would only record the difference between the pair of you. So the difference between me and my wife would be +5 years, and you and your husband might be -2 years, because sometimes the wife, you know, is older than the man, or vice versa. And those single numbers, right? +5, -2, +3, 0, -7. Those are the paired differences. So when you do a paired difference, don't you just end up with a single set of data, the average difference between them? So that would be what it would look like. And so you might say, well, how do you treat that? Basically, you take your data and you subtract them and you get a whole list of numbers. And then you treat that list of numbers as a single population. And it can tell you things like, well, I can tell you right now, do you know that typically that if you look at a husband and wife combination, the husband typically is about 2 to 3 years older on average than the wife, right? Now, is there exceptions to that? I guarantee there's exceptions to that. But in general, that's the truth. So, Maggie, you are smiling. Is your mum older than your dad, just to prove me wrong?
No, my dad is 13 years older than my mom.
Okay, so he's older, right? I won't ask any other people personal questions. It's not a big deal, right? As long as it's not like 30 years old. I got to get this out of my head because it's in my head now. Have you ever seen those really ugly rock stars? I mean, they are ugly, right? They're like shriveled prunes that have been preserved in pickles. And they marry a 25-year-old model who's gorgeous. And I'm thinking to myself, she didn't marry him because of his looks. I'm just putting that out there, right? Because if he was a shriveled up prune, but he worked as a car mechanic, do you think that 25-year-old model would have married? Maybe well, I can't say I'm jealous because I'm happily married, but whatever. Random thought, got it out of my head. I feel much better now. For each part, write and define the notation that would be used. Okay, so in this story, the one about the speeding cars, wouldn't the population of interest be mu, the population meaning the mean of all cars that use that street? And this population mean of all the cars in this area, which is that answer. And suppose you wanted to do the before average and the average, wouldn't it be this guy? And that's the difference. So basically, isn't that a bit like the first step, H naught and HA, right? Now, question 3, and I think also question 4, only gets you to do one thing, and that is it gets you to calculate the t-score. And there's a lot of numbers that you use, but can you see they're all there? So it would be 38 take away 35, right? That's the x1 bar take away x2 bar. And wouldn't you get the standard error by using those two numbers along with those two? Do you want me to do that calculation, or are you comfortable about you would do it yourself anyway?
I'd rather you explain part B.
Ah, okay. Now
Yeah.
in part B, well, before I continue, Cody, what were you going to say?
No, I just said ditto or same. Part B.
Okay, gotcha. Now in part B, they've actually made your life easier, even if you don't know it, because the difference between them is 43, and you divide it by the standard error, which is 24. So you don't need to take x1 bar take away x2 bar. They told you what that number is, it's 43. And you don't need to calculate the standard error from scratch because they told you it was 24. So isn't that the difference on the top divided by the standard error on the bottom? And that'll end up being 1.78 or 1.79. So a lot easier than you thought, right? They gave you more information than they typically would. Now, in this question, all the information you need to know, you're going to get from up here. So to get the t statistic, won't I have to take x1 bar and subtract x2 bar? So that would look something like this. 80.55, that's the first mean. Take away 78.51. That's that bit. And then wouldn't you finish by dividing by the standard error? Right. There's too much going on there. Let me just do it, I think. So we're going to calculate the t-score from a set of data that's given in the question. So it's going to be x1 bar take away x2 bar all over the standard error. Where I've been told that that's the value for the first mean. This is the second sample, this is its mean. So x1 bar take away x2 bar is just going to be that take away that. So I'll do that in my calculator. 80.55 subtract 78.51, and that's 2.04. So 2.04 goes there. Now you want to get the standard error. You use this formula, the square root of S1 squared over N1 plus S2 squared over N2. All these numbers are in that table that you can't see anymore, but it ends up being 4.26 squared over 66 plus 3.36 squared also over 66. And if you do all that in your calculator, let's see what we get now. Square root of 4.26 squared divided by 66 plus 3.36 squared divided by 66. And I get about 0.668. And if you take that guy and divide it by that, you're done. So 2.04 divided by 0.668. And the answer is, to 2 decimal places, 3.05, which is exactly what it is in WebAssign. Is that looking good? Any questions before we move on to number 5, which is basically halfway through? Are we comfortable about getting T-score if you tell me all the numbers that I need? So I've got the mean out of the way, good. You never find things where you want to. Here we are, this is question 5, found it. Now, in question 5, you have a whole load of data at the top here. So let's see the context. A set of body temperatures was taken for 100 adults at a blood donor center. And this is done by a piece of software called Minitab. You know, Salt does the same kind of thing. And it shows the output from the results of 2 samples, T procedure, comparing the body temperatures of females against males. Population 1 is going to be the females, which just makes sense, it's the top row. And population 2 is going to be the males. So let's see, if you just look at the mean body temperature, women are a little bit higher than men. Now, I don't know if that's just this sample. Anybody in the nursing world, are women's bodies a little bit warmer than men's bodies? Is that a typical thing? Or are they both the same?
I don't know, my body's like an oven, furnace.
Well, that's just because you're sick. You've got a fever. I don't. Okay, let's just assume then that there is some detectable difference between males and females. And the difference between females take away males, right, is 0.293. So if you took this guy and you subtracted the one here, that's the answer. They've got a confidence interval for what the difference between the two would be. Do you notice that that confidence interval only has positive numbers in it? Isn't that evidence then that women have warmer bodies than men, right? The t-test that we're using has a t-value of 2.06, a p-value of about, 4%, and just for fun and giggles, they even told us what the degrees of freedom are, although half these numbers we're not going to use. Now, let's set up a null and alternate hypothesis to see if there's any evidence to prove what. Let's see. I do not know. Well, let's put in the one I do know while I'm thinking. I need to put in mu1 take away mu2 is 0. That's the standard null hypothesis that everybody is going to get. There's mu. Subscript 1. Take away mu subscript 2 equals 0. So the null hypothesis is saying there's no difference between men and women, right? The difference is 0. There is no, they're the same. Now, what I can't see here is this a bigger than, a less than, or a not equal to? Is there somewhere in that sentence that I've just skipped and scanned over? Because I cannot see.
Not equal to?
Yeah. Where's
Because you want it to be, or do you see something? I'm not saying you're wrong, because I can't tell. That's what's puzzling me.
in the
I only guess because it doesn't specifically say whether it
Anything.
wants them to be more or less.
I think that's probably the best route you go then. Let's do that. Copy.
Mr. Robertson,
Yes.
wouldn't it be because in the t-test of difference it says versus not equal?
Is it say it somewhere here? That bit there?
In the information where it gives you the t-test. it says-
Oh, here we go. There it's hidden. You see it there? Versus not equal to. Well caught. So we were going to get the right answer. Maybe not for the right reason, but we were going to choose the right one. You have to do exclamation mark equals when it's a not equals to situation. It's weird, but that's what you type. Now it says, what is the value of the test statistic? Well, the test statistic is here. It's called, one of its many names, it's called the t-value. And then they give you something a little bit different. They give you lots of boxes where you're meant to be putting in the numbers that would calculate the t statistic. Now, shouldn't the top be x1 bar, take away x2 bar, right? x1 bar. So I'll go up here and I'll find x1 bar, which is this fella. I wouldn't need to copy it, I just need to know what it is. 9.83. But I'm going to have to shrink this a little bit so I don't have to keep scanning up and down all the time. One more, maybe. Right. So it's 98.3. So 98.302. That one. Take away the guys, 98.09. Right. Here, select 0.766, okay. 0.766 over 47, yep. 0.657, I got that wrong. And then it's 0.766. And the whole thing should equal, what was that number again? It should equal 2.06. So do you see what they've got you to do here in its rather clunky way? Haven't they got you to write down the calculation that you would have used to get a t-score? You know what it is, but they're just saying, could you show me how you would do it if you were putting in numbers? Now it says p-value. Well, that guy is here. Now, isn't that less than 0.05? So we've got evidence that women's temperatures are actually different from men. So if the body mean temperatures are, what's this? If the population mean body temperatures are for female donors compared to males, well, they're greater. The probability of observing a difference is the p-value. So where's the 0.04? Where's that coming from? Probably observing a difference. There's the difference.
The answer for the first part is the same, but I can't figure out why.
Well, I know it should be this fella. I just can't find the guy. Where's the p-value? What have I misread? No, the p-value's here. Okay, let's find out their answer and work backwards.
Would it be asking for the difference since that seems to be the same number?
I'm going to turn the sound thing up. I think I'm getting. I didn't quite catch what you said, sorry. Oh. So they are saying the 0.293, and the 0.293 is from here. Okay. So if the population mean body temperatures are greater, so they're saying the same for female donors compared to the public observing a different.
How did you find the p-value?
P-value was up here.
Oh, okay, there.
There. So they're just doing it in terms of the difference. So the difference could be that one, or I guess the opposite. And no action is required. Well, that's typically the go-to answer in that question. Although I don't know if you knew for sure that there was a difference between males and females, if you were measuring someone's body temperature, shouldn't you take that into account, that a woman could be a little bit warmer and she doesn't have a fever, right? Or a mild fever. But they didn't give us that. So question 6 is essentially a carbon copy of the one that we just did. So do you see it's the same kind of data, the same kind of setup. So I want to skip by that one. And let's do for the last, the last 3 questions. We are going to do the whole process using SALT. So I made up my own little question because I don't want to use up, practice so you can do your own. So the blood pressure of 200 people was taken and the mean was 120 with a standard deviation of 5. They were given some medication and their new blood pressure was now 118 and the standard deviation was 20. Is there enough evidence to prove that the new medication reduces blood pressure? So that's our story. And we are going to create at the significance level of 5%. So the first thing I would do is set up the null and the alternate. Population 1 are the people who didn't have the medication. Take away what happens after. And if there's no difference, you'll get 0. The alternate before, that's population 1, after this guy. So the alternate would be that this guy is greater than 0. Which you can see it. Population 1 is greater than population 2's mean. So another way of saying that isn't that the first thing is bigger than the second. Of course, isn't that also the same as saying the second thing is smaller than the first? So this would be what you would be looking to see if this medication did in fact reduce blood pressure, right? It looks like it reduces it by 2 units, okay? So what we would then go on and do is get our t-score, get our p-value, and we would get both of those by using SALT. Much quicker and much more accurate. So I'm going to go in, and this is kind of going to be our last question for today, so we can finish this off tomorrow. We hit this fella, and we're going to do a 2-sample T. Where am I? Oh, there we are. Click on it. The first group, the people who weren't on medication, had a 120 they had a standard deviation of 5. And there was 200 of those people in that group. And then they took a medication and their blood pressure went down to 118. And the standard deviation was 20. And of course, it's still 200. So we're doing it that way. And I could have done this as a paired difference, but I'm not going to do it that way. We're only going to focus on the typical difference between. And hypothesis test, that's 0. We're trying to prove that the first thing, right, the people who didn't have the pill, is bigger than the other one, and generate results. And the T guy was 1.37, and the p-value.
I thought we were trying to prove that it does less than. It
We're
lowers the
trying.
p.
Well, it's the English language. Well, I want to prove that the second thing lowers it, but that's the same as the first thing being bigger than the second thing. So mu1 take away mu2 greater than 0 means the first thing is bigger than the second. That's the same as showing that the second is smaller than the first. Okay, analogy. I'm bigger than my sister Mary. My sister Mary is smaller than me. Aren't they the same information written in two different perspectives? So mu1 is the before, mu2 is the after. If the difference between them is a positive number, that means the first thing is bigger than the second. And isn't that the same as saying the second thing is smaller than the first? So that's a long-winded way of phrasing it. And our p-value came out to be 0.085 roughly. So those two numbers would be how you would do it in your test, right? You'd write this down. These two, although it's pretty obvious, you could just write down salt, so I know where you got them from. Now, conclusion time. Is our p-value less than alpha? Is our 0.085 less than 0.05? Yes or no? Is that true? No. And when it's no, don't we get the various ways of phrasing that? One way would be not enough evidence to reject the null hypothesis. Couldn't we also say there's not enough evidence to prove that the new medication does any different, right? It doesn't help. And perfect timing.